So we looked at function transformations a little bit yesterday. Your warm-up should have looked like that. If I have the graph of this function f of x and I want to graph f of x plus 2 minus 1, first off, think about the fact that if you're changing it to x plus 2 for your input, that's actually going to translate your function left 2, and the minus 1 on the outside is going to translate it down 1 for all of its points. So if I want to graph my new function, one way you could do it is just take a point on your original function and count over left 2, down 1. If you pick the ones that are on nice grid lines, it makes it a little bit easier. So do some here. Make sure that you do enough points so that you can get the full shape of your new translated function. And then draw in your line and connect them. So my new translated function, f of x plus 2 minus 1, looks like that in green. If you don't have a graph, or if it is just easier because some of your point coordinates are kind of messy, you can use a table of values. So I'm going to look at the transformation g of x minus 3 plus 1. Inside of my function g of x, I'm going to have things translated right 3, and the plus 1 on the outside moves it up 1. So if I'm moving right 3, think about how that changes your x coordinates. X is left or right, and to the right on my x-axis, it's going to make things bigger, so I'm going to add 3 to my x coordinates. And if I'm translating up 1, that's going to increase my y values by 1. So I'm going to take all of my points for g of x and add 3 to their x coordinates to translate everything right 3. And then I'm going to take all of my y values for g of x and add 1 to translate things up 1. And that'll give me my new coordinates for my transformed function g of x minus 3 plus 1. There are other kinds of transformations besides moving things left and right or up and down, and we're going to look at some of them. So we're going to use the function f of x equals absolute value of x plus 1, and a table of some of the points on it is given to us right there. So what I'm going to do first is look at my function g of x where I've changed it so it has a negative 1 being multiplied by my original function's values. So the easiest way to do this is to use your table of values that you already have for f of x, and g of x is just negative 1 times those output values from your original function, because you already have the values of absolute value of x plus 1 up there. So let's just take negative 1 times all of those. I could go through and plug in the x's and get the y's out using my absolute value function, but let's work smarter, not harder here. And then if I plot those, it's going to give me an absolute value function that looks like that. So if you notice what's going on here, it kind of opens upside down. What I've got is actually a reflection of my original function across the x-axis. My original one, if I kind of draw it dashed in red here, looked like that. This essentially changed the signs on all of my y values and reflected across the x-axis. Let's take another one. So this one actually has a negative 1 multiplied by your x values. So if I want to make this as easy as possible, I'm just going to take my original x values and change the sign on them, because that's essentially what this function is compared to the original, is a negative 1 times my x values. And then my y values, you could plug in those x values that I have right there and get out the appropriate y values. You could also recognize that your y values are going to be the same as on your original function. So if you don't want to go through all that work, all this function is different from my original is it's changed the signs on my x's. My y values are going to remain the same. So my new function is going to look like that. And if you compare it to your original, it's kind of hard to tell, but this is a reflection across the y-axis. Every point is flipped across the y-axis on this one, which kind of makes sense because we changed the sign on all of our x-coordinates. So if we make a couple of generalizations here, if you Change your function so that it is -1 times your output. It reflects your graph across the x-axis, and -1 times your input reflects across the y-axis. So if you kind of think about a point, first situation changes the sign on your output or y. Second situation changes it on your x's, your input. So say you have the point 1, 2. If I have it so that I change the sign on my y-coordinate, then that point is going to get flipped across my x-axis. If you go the other way and change the sign on my x-coordinate, now I'm going the opposite direction horizontally, it is going to flip that point across my y-axis. So if you can't remember which is which, just draw yourself a picture. We're going to do some transformations on square root of x. So some of its points are listed in that table right there. Our function that we're looking at first is g of x, which is 2 times square root of x. So really, to get points for this, if you want to take the easy way, let's take 2 times my square root of x points that I have already calculated from my function f of x, because f of x was the square root of all those x values. So if I take and multiply 2 times all of those will give me my g of x coordinates. And then if I go ahead and graph them, looks like that. Comparing that to my original function f of x, all of my y values are essentially doubled because I took them times 2. So it is twice as tall vertically, and that is a vertical stretch, or a vertical expansion is what they call that. So it's a vertical stretch by a factor of 2. All my y values got doubled. If I take a look at h of x, you might be able to predict what's going to happen. This is 1/2 times the square root of x. So I'm going to take 1/2 times all of my original coordinates for square root of x, which I just pasted in there. So if I take 1/2 times all of those output values, my new points for h of x are going to be all of those with my y values cut in half. So it is going to be kind of shorter and flatter than my original function. So that is called a vertical shrink or a vertical compression by 1/2 or by a factor of 2, because it basically shrunk it vertically. It's only half the height as my original. So making a couple of generalizations. Transforming a function by multiplying its output by a value where its absolute value is greater than 1 is going to make it a vertical stretch. Multiplying it by a value that has an absolute value less than 1 is going to make it a shrink. That absolute value is there because if you think about something like this, that is still a vertical stretch. It's going to stretch it in the opposite direction because it's also reflected across the axis, but it's still going to be a stretch even though if it's a negative number. Okay, our last type of transformation. We are still looking at square root of x for my parent function. This time my 2 is being multiplied times x inside my radical. So what would make my life easier is these points are picked so that they give us nice values when I take the square root of them on my parent function. I would like them to give me nice values whenever I take the square root of 2 times the x value that I'm using. So let's make the inside of my radical equal to the original by going, okay, what would get me 1 inside my radical? Well, if I want 2x to equal 1, I'd have to divide by 2 and get 1/2. If I want 2x to equal 2, I'd have to divide by 2 to get 1. So essentially, if I want the same nice values when I take the square roots in my new function, I have to undo the fact that I'm multiplying by 2 on the inside by dividing all of my original x values by 2. And then if you run through and try it, well, if I took the square root of 2 times 0, square root of 2 times 1/2, I'm going to get the exact same output as I had on my original parent function. So really, I could just copy those y values down from above and not even calculate them. So if I graph my points for square root of 2x, you have to be a little bit careful here because some of them are kind of close together. Since essentially it's my original function with all of the x values divided by 2, This is a horizontal shrink because everything kind of got compressed backwards. It's only expanding half as far out horizontally as it would have on my parent function. So that's a horizontal shrink. It's kind of backwards to think about because I know you have 2 times x inside there, but we're thinking about offsetting that, and that actually means you cut your x values in half, divide by 2. This one, same idea. If we want to make it as least work possible, let's keep it so that our y values will be the same, which means I have to offset my fact that it's 1/2 x inside by figuring out what x values will make me match my original. So if I want 1/2 x to equal 0, that's still a 0. If I want 1/2 x to equal 1, that gives me x value of 2 and 4. So essentially what I'm doing in this case is to offset that 1/2, I am dividing by 1/2, which is the same thing as multiplying by 2 on all of my original x values. So if you multiply all my original x values by 2, you're going to end up with 0, 2, 8, and 18. That was an ugly 8. And then that will give me the same y values as on my parent function, and I don't even really have to calculate them. You could if you want to convince yourself. I'll do it for 18. But all of them are going to be the same. Which, if you plot them, it's actually going to take longer horizontally to match my original function shape because I ended up doubling all of my x values. So this is a horizontal stretch or horizontal expansion by a factor of 2. All right, so let's make some generalizations. Since we are changing the input, these are going to be horizontal expansions or compressions. And if your value of your coefficient on x is greater than 1, it's going to give you a horizontal shrink because you have to think about offsetting what's happening. So if you divide by a number bigger than 1, it's going to shrink it. And then to undo your multiplication, if you have something less than 1 and you divide by a fraction, it gives you a value that's bigger, so that'll be a stretch or an expansion. Okay, one where I've got a whole bunch of transformations happening. So my goal is to get to this final transformed function. I want to start and kind of follow order of operations here. So work inside of my grouping symbol and first translate that function to the right 3, which means I need to add 3 to all of my x values. That's not changing my y's if I move it to the right 3, so I'm just going to write my originals back. Oh, I actually realized I broke this down here. Whoops, hang on. I meant to have it in this table down below. Okay, so next transformation that needs to happen, I multiply before I add or subtract order of operations. So if I multiply those values for my output, my y values times 2, it's going to be a vertical stretch. So I'm going to take my y values for my function and multiply them by 2. Since I'm just doing a vertical stretch right now, that doesn't change my x values, so I'm going to copy them from my previous step. And then the last thing that I need to do is my translation of moving things up 1. So if I translate up 1, that's going to change my y values by adding 1 to all of them. So let me take my progress so far. I'm not changing my x's. I'm going to add 1 to all of those y's. And then I should have my final transformed points for my function that I was trying to get. And I guess I'll go back and put them up at the top where I had my table for my final values. So there we go.